Okay, here's the Chapter 11 Summary You Try It problems. Let's go ahead and try these and see what we can learn from them. Some of them may be hard, but remember, you learn from them. What is the product of the SN2 reaction of hydroxide and the R compound, where, notice, this is the carbon that has the iodine on it, and what's attached? A hydrogen and a deuterium and a methyl group. So this is a chiral compound. The carbon that has the iodine is right here. Figure out what is the product of this. Since this is an SN2 reaction, we're going to get the S compound. There's going to be inversion. It's going to be the S compound, and you're going to have the hydroxide displacing the iodine. So if I go ahead and look, I have to just go ahead and look at each of these compounds and identify what is the chirality of each. This one right here, this is going to be R. This one right here, we don't have the iodine being displaced, so let's toss that one. This one, what is the chirality of the compound? This one's going to be S, so it's probably this one. Notice here, we're not even displacing the iodine. Here, we're not even displacing the iodine. So the only one that's the product is this one. So what is the absolute configuration of this product after this reaction occurs? When you look at this, you probably are looking and saying, well, I'm going to have inversion occurring, and so I should go from S to R because it's primary and I have a nucleophile displacing. But notice, the chiral carbon is this one right here, because the chiral carbon is not where displacement is occurring. The product is just going to be S. Which of the following SN2 reactions is expected to have the highest rate? Okay, let's go ahead and look at each of these. We've got methyl bromide, ethyl bromide, ethyl bromide, ethyl chloride, and methyl bromide. Well, let's just look and just right off the bat, I'm going to say methyl bromide probably is going to be a faster SN2 because methyl is faster than ethyl. There's one less carbon there to get in the way. So for steric hindrance, methyl bromide is going to be faster. Then if I look at water versus hydrosulfide. The hydrosulfide is a better nucleophile than water. DMSO and HMPA are both great SN2 solvents. So what's going to be the product, the fastest reaction here is going to be number 5. Okay, with the information given to you right here, what type of reaction occurs? Well, first thing, I look at this rate equation and I see there's 2 things in it. So automatically I can eliminate E1 and SN1. It's going to be E2 or SN2. I then look at A and I see it's primary, and B and I see that it is a bulky base. And when I see bulky base, even with primary, I think E2. But then I go back and I look at this product, and if I form a double bond here, that's going to put 5 bonds on this carbon. There's no hydrogen on this carbon to react in an E2 reaction and form an alkene. So an alkene can't form, so E2 can't be occurring. What is the mechanism for the reaction? SN2. So now we see that the product would be that this T-butoxide is going to displace the O-tosyl group to form this ether. So what is the main reason that polar protic solvents are favored for SN1 reactions over polar aprotic solvents? Well, let's look at the possibilities here and see if we can eliminate some. Okay, in this first one, it says polar product solvents are not basic. Well, some polar product solvents actually can be basic, but that's not the reason that it favors the SN1 reaction. The reason the SN1 reaction requires a polar product solvent is really for making the energy of the transition state lower. Polar product solvents destabilize anions. Well, that's not true. They can hydrogen bond to an anion and stabilize it. That makes it so that this actually encourages an SN1 to react when it stabilizes the anion. Polar product solvents form stabilizing hydrogen bonds to the cation. Well, there's no way that a cation will hydrogen bond to a solvent. The hydrogen has a del plus, which will not be attracted to a cation. Polar product solvents prevent rearrangements from occurring. Well, that doesn't happen. They don't prevent that. They stabilize a carbocation, and they might actually encourage rearrangements to occur because it might make the carbocation last longer. What's the key point? Polar product solvents hydrogen bond to the leaving group, stabilizing that anion so that the carbocation can form more easily. And then the polar part stabilizes the carbocation. But the product hydrogen bonds to the leaving group. So which of these statements about the SN2 reaction of methyl bromide with hydroxide is incorrect? This is actually a very hard problem because we'll just go through these one by one and you're probably going to learn a lot from it. First of all, the reaction kinetics is first order in hydroxide. And probably when you looked at that, you said first order, well, it's SN2, so it's second order. But it's second order overall, but first order in hydroxide and first order in methyl bromide. So the first statement is true. In the transition state, the carbon is sp2 hybridized. Well, if you look at the transition state, the leaving group is mostly gone, and the nucleophile has not yet come in, and the carbon is planar. And sp2 is planar, and you have a p orbital that sticks out perpendicular to the plane. And so we can look at the transition state and say, since the bond to the nucleophile has not yet formed, and the bond to the leaving group is breaking, the carbon can be thought of having a del positive on it. We consider the carbon to be essentially sp2 hybridized in that transition state. That was a hard one. Absolute configuration is inverted from R to S. Well, methyl bromide is not chiral, so how can the absolute configuration be inverted? That's the one that's incorrect. Let's look at this. The reaction is faster in HMPA than in water. Well, HMPA is a polar aprotic solvent and water is polar protic. SN2 is faster in HMPA because it's polar aprotic. The reaction can be catalyzed by iodide. This is actually correct. Methyl bromide can undergo an SN2 very quickly with an iodide. And then what happens is the iodide's a better leaving group, so the hydroxide then can attack the methyl iodide even faster. And so this is actually true. So the answer to this is that the absolute configuration is inverted from R to S is incorrect. Okay. Because methyl bromide isn't even chiral. These are conditions for a substitution reaction. Which one would react fastest? Well, and when I look at these, the first thing I do is I look at the conditions and I say, wow, the conditions look like they're for an SN2. Why? Because we've got a polar aprotic solvent and a reasonable nucleophile. Then I look at the carbon compounds and I see they're either secondary or primary. And again, I think, well, this looks like SN2. So first look at the conditions and say, is it SN1 or SN2? And it's SN2. Now, which one of these is going to react fastest in an SN2? Well, primary is faster than secondary, so I eliminate the secondary. That leaves me these groups are left. Which one of these groups would be best? Well, the iodine has this group right here that's going to kind of cause a little bit of steric hindrance, so it's going to slow down. Then I compare the bromine to the tosyl. The tosyl is a better leaving group, so the compound that's going to react fastest will be this tosylate. Which electrophile will react fastest by an SN2 reaction with cyanide in DMF? Well, if I go to these compounds, first I see phenyl iodide. That means there's a benzene ring and the iodine's attached directly to the benzene ring. That's not going to go at all. Then I look at the tosylate. It's on a carbon that is in a double bond. That's not going to go at all. Then we have the ethyl bromide, cyclohexyl bromide, and benzyl tosylate. The cyclohexyl bromide is secondary, and ethyl bromide and benzyl tosylate both are primary. The benzene ring, the phenyl ring on this carbon is primary, that's primary, but this helps to stabilize the transition state. So the fastest one is going to be number 5. And so it's not even circled, but it's number 5. Which of the following reagents is the best nucleophile for an SN2 reaction? Well, if I look, I will see that there are several neutral nucleophiles and several that are charged. The charged ones with a negative charge are automatically going to be better than those that do not have charge. So 1 and 5 are eliminated as being the best nucleophile. I then see methoxide, acetate, and hydroxide. The acetate has a carbonyl and an oxygen, and it's resonance stabilized, and so the acetate is not the best nucleophile. Acetate is the weakest base there. Methoxide and hydroxide are stronger. Hydroxide is weaker than methoxide, and so the best nucleophile is going to end up being methoxide. Which set of reactions will be the best way to carry out this conversion? Well, if I look at this, I can see it's got to be an SN2 reaction because we have inversion at the stereocenter. So if I have this nucleophile, it's protic, and so it's going to encourage an SN1 to occur. So I'm going to eliminate all of those that have protic solvents because they encourage SN1. So it gets down to these two. If I look, this is a protonated, this is acetate, by the way, the OAC. This is acetate. This is acetic acid in HMPA, and this is sodium acetate in DMSO. The sodium acetate has a negative charge, and so is a better nucleophile. So we need inversion because it's so we're going to need SN2. We want to have an aprotic polar solvent to have SN2. The negative nucleophile is better, so the sodium acetate in DMSO is the best choice. Which of the following will give the fastest SN1 reaction? Okay, right off the bat, I look and I say this will not undergo any kind of nucleophilic displacement, so we're going to eliminate that. This is tertiary, this is primary, and that's secondary. Well, these are actually pretty fast, but not as fast as the tertiary. They're fast because they're stabilized by the pi system nearby. If I look at this is secondary, and it's got two pi systems attached. The fastest one is going to be the most stable carbocation. The phenyl, of course, is unreactive. Tertiary is good, but the conjugated is better, and this doubly conjugated is best of all. So that one would react the fastest. In a reaction between an alkyl halide and a methoxide, what can we conclude if doubling the alkyl halide concentration causes the reaction rate to double? Well, all of these processes, SN2, SN1, E2, and E1, will be doubled if you double the alkyl halide concentration. So just because doubling the alkyl halide concentration doubles the rate does not give you any idea what's happening. You can see there's methoxide in there, so it's not going to be SN1 or E1. But at the same time, SN2 and E2 both are possible, so you really can't conclude any of these. So the correct answer is none of these. Which of these compounds would serve as the best starting material for the following transformation? Okay, if I look at this, I'm going to be using sodium hydride, a strong base, to form an alkene. If I look at this, I'm going to try to, if I use the strong base on this compound, I'm going to form a more substituted alkene. If I use a strong base on this compound, I'm going to get a double bond right here. A strong base here, well, that's going to end up deprotonating this hydrogen here. Same with this. The only one that would cause the double bond to form here is if you treated this compound with sodium amide, because the hydrogen here would be removed when the bromide left. Including stereoisomers, how many products are possible from the following reaction? Well, let's go ahead and look at what we think will happen here. We've got base, strong base, and we've got a secondary carbon. So we're going to have a lot of elimination occur here. Where can elimination form? It can form on this part of the compound or on this part of the compound. So we will get either a 2 or a 3 hexene. But for each of those two compounds, we can have either the cis or the trans compound form. So that gives us 4 compounds right there. But SN2 can occur also. Even though it's going to occur slowly, there's going to be a little bit of this made. If SN2 occurs, what's going to happen? You're going to have inversion on that center. And since this is the S enantiomer, only the R enantiomer would be made. So how many compounds would be made? What mechanism is most likely to operate in this reaction? Well, remember what I told you about halogens that were 2 carbons away from a carbonyl. Halogens that are 2 carbons away from a carbonyl are going to undergo a special mechanism. Well, you can see right now it's got to be either E1, E2, or E1CB because an alkene forms. Which one is going to occur? You do have base, but we've got E1CB occurring because you've got that carbonyl there. So, since the double bond forms, is it substitution or is it elimination? Well, it's definitely elimination. Since the bromine has to be 2 carbons away from the carbonyl, can it be E1CB? Since base is present, which one's more likely? E1CB. Select the reagent and solvent which would result in the fastest rate of substitution here. Well, since this is primary, we're going to want to have conditions that would give SN2. So I look and I can eliminate any of the protic solvents. I see this and I see this are polar aprotic. The alcohol is not as good a nucleophile as this negative thiol, this thiolate right here. So what do we pick? Primary means SN2. SN2 is faster with polar aprotic. That throws out the water. Nucleophile with the negative charge is better. Larger atom, sulfur, is bigger and better than the oxygen. So the fastest reaction would be this one. Which of the following is the best nucleophile? Well, if I look at these, the best nucleophile is going to be one with a negative charge and one with a bigger atom. Phosphorus is a bigger atom than oxygen, so we choose that one. What is the product of this reaction? First thing you do is you look and you see secondary carbon, strong base. Elimination is going to occur. It's going to be E2, so you rotate this around until the hydrogen is opposite the tosylate. That's going to put the phenyl on the same side as the methyl. So I look for an alkene. The leaving group has to leave, so we toss that one. Why is it I'm choosing the tosylate as a leaving group? Because it's a better leaving group than the chloride. So this gets tossed out because the tosylate's a leaving group. Chlorine's going to still remain in there, so we have to eliminate this. We look at the last three here and we see phenyl will be on the same side as the methyl if we rotate this to the anti-periplanar, and we end up with that compound. What is the product of this reaction? Right off the bat, I see the T-butoxide and a secondary carbon. I know it's going to be an alkene. If I look at the chlorine, it's down, and the hydrogen on this carbon is down. So you can't get the anti-periplanar arrangement to give you the alkene in this position. So I know it's going to have to go to this position. So I look, and the compound is going to have to remain with this up and this down because those are not involved in the reaction. So I look for this up and that down and the alkene right here. This and this are eliminated. This is eliminated and this is eliminated. It's going to be only this compound.